Then we will start. So if you recall, before our break, we discussed the theory behind the dimensionality reduction. So dimensionality reduction. And we discussed majorly two approaches. One is PCA. So PCA is principal component analysis. And this is for unsupervised learning. Okay, and the second one that we learned is LDA, is linear determinant analysis. Okay, and this is for supervised classification. Okay, so we discussed the theory behind them. So, so what we are going to do today is let's take a look at the examples. Okay, using PCA. The first one that we will take a look is going to be on the MNIST. And if you recall, the MNIST is for handwritten digit. Digits training, if you recall. Okay, so let's take a look how, and if you recall previously for this traditional MNIST data set, the dimensionality is quite large. It's 784 because it's 28 by 28 pixels. Is it so? The feature is very large. It has 784 features. Is it? And the total samples is about 7,000. Okay, that's the data set. And there are multiple ways for you to import the data set. Okay, and previously we also learned. So we can also, sklearn also has that data set, and you can directly import it to use. Okay, so that's nothing new here. So we get the MNIST data set. Okay, and the shape analysis. So we already saw it a couple of times in the previous chapters, is it? And the shape, okay, for the target. So target is 10 digit, 0 to 9. Okay, this is as usual, we do training and testing data split, okay? So nothing new here. And then we just check, okay, about the training data set size, is it, and the testing data size. Okay, and what is the next part? If you recall previously, we also discussed, is it, and for the MNIST, so each data sample, so it has totally 784 features. So basically the columns, their columns. But for image, for the 2D image, we needed to display it as a 2D image as a 28 by 28 pixel. Is it over here? For this part, it's just use a pie plot to show the image. Okay, to show the image. That's why for each, because each of the image, you get it from the, we are going just to show the top 5 training handwritten digit. That's the top 5 one. Okay, and the original is 784, is it? And we need to convert it to 28 by 28, is it? So that's why over here you need to reshape it, is it? And then you show the image. Okay, so that's, we get to the top 5, is that the training digit. Okay, and over here, I also showed the, this is the second one. Okay, the second one, let's take a look. The second one, sample, the digit is 1, is it? And digit 1, basically, in the training data set, what it is showing, you can see, is it? It's just some numbers. There's some numbers, is it? So it's number between 0 to 255, is it? You can see. And a lot of zeros, is it? And you can kind of see it's kind of like that 1, is it like 1? And over here, the combination of the numbers will give you the pixel value so that you will be able to see the image, okay? Okay, so that's just one sample data, okay? And what over here we are going to see is about how we apply the principal component, is it? And what over here for the principal component object when you initiate, and what over here we passed in is a certain percentage, is it? And if you recall, the percentage represents the explained variance over the total variance, is it? So here we just want to maintain 95% of the total variance, is it? After you do the dimensionality reduction, you can still keep 95% of the variance. So that's our goal here. Okay, so you can plug in. So for PCA, you can specify the percentage of the explained variance that you want to keep. Okay, and then we can fit the training data set. And after this, from sklearn, you can also get the number of components, the principal components, after we apply this PCA. Okay, then in this case, it's reduced to 154 principal components. Okay, and of course, among the 154, the first one keep the most percentage of the variance, and the following the second one, following the third one, and they are orthogonal, etc. So that's a definition for PCA, the theoretical background. Okay, and so just some idea about PCA, is it? And then you can transform your data, is it, for the PCA, is it, for the PCA. So then this is projected. So basically this is projected data value, okay, to the principal, in this case, 154 principal components. From the original, it's 784, is it? It did reduced, is it? And sometimes you may want to also reverse it back to our original high dimensional space, is it? And you can also do it with sklearn. It's called inverse transform. Okay, then we get to the approximation, okay, of the original 784. Okay, but it's not completely because you already lost 5% of variance, is it? And then we can show the original image and the 154 image. Okay, so over here is just this is the original image with the 784 components, and this is the reduced one, is it? And it maintains this percentage of variance, is it? And then you can see with the image, is it? It's a little bit of blurry, but it's still recognizable, is it? So it's still pretty good, is it? But we can see we did reduce the number of features a lot, okay? Okay, and what is the next one to show is over here, if you initiate the PCA without any input, then it's going to keep all components. Okay, so 784. So keep the original basically. If we didn't pass in any percentage or number of components, okay. And then what next one try to show is the explained variance, is it? And if we sum them up, what we will get, is it? So all of the variance, is it? So that's all of the variance. And what the next one try to show is you can sort it, the variance, is it? And then over here, we take the top 5 of the variance. So basically, this is the first principal component, is it? Okay, and you can also see the cumulative variance. Okay, so here is the cumulative variance. So for the cumulative, then we are going to have a plot regarding the cumulative variances and the individual variance, so that we can understand. Okay, so we are going to plot the explained variance. Okay. And so over here, so we have some comparison, is it? So this one is our cumulative, okay, explained variance. So the x coordinates is a number of components, and the maximum is 784, is it? And our tried one with 95% of explained variance is about 154. Is it 154? And 154, so the y-axis, okay, the y-axis is cumulative one. Okay, so cumulative. It's about the percentage, is it? So this is about 95%, we can see, is it? And it also gave us the comparison about like 90% and 85%, is it? So this is about cumulative variance, okay? And then we can also see the number of components, is it? Number of components for the different percentage of explained variance here, okay? So if you want 100, that's 785, is it? And 95, 99, and 95, and 90, and 85, the number of principles, is it? So you can see it's reduced quite a lot. And this is quite straightforward, is it? And what is the next one try to show us? Over here is define a function. Okay, so what the function is going to do is it's going to take a different percentage for the explained variance for the PCA, is it? And then you try to feed the data, is it? And you transform the data. Okay, then we call that inverse back to the original dimension space, is it? And we can get to the original, not original. So this is the with the percentage. Okay, the percentage, so like 95%, 90%, or 85% of that explained variance, is it? And then we have like 154, then maybe this is 90, maybe this is 55 principal components. So with those number of principal components, that means you reduced, you filter out quite a number of features. There are quite a number of features because previously you have 784, is it? Now maybe for the 85, you only have 55 columns, is that column? But we want to project it back to the original 28 by 28 pixel space to display our image, is that? So that's what this function try to do, is it? And with this function, then we are going to try to do the plotting. Okay, the plotting with our original one and with the reduced number of principles, is it? And then we show our image. Okay, show our image. So this is the image, is it? And reshape it. Okay, and then let's see the result. So here we have different level of the PCA, is it? Number of components you can clearly see, is it? You can see even with us to maintain just 85% of explained variance, the digit you see, even though it's much more blurry as I compare with 95, but it's still recognizable, is it? So that's why we also see PCA a lot of time can be used for compression. Is it to save storage space? Is it? So that's also one of its usage. Okay, and what next we try to see, how do we then use PCA to speed up machine learning algorithm? Okay, here we are going to take a look for the logistic regression. Okay, because keep this in mind. Okay, logistic regression is for classification. Be careful, okay, linear regression, even though both have regression name, but this is for continuous value prediction. It's not for classification, okay, be careful. So when you compare, you should compare the algorithm. If it's for classification, then you need to compare. Don't use different category to do the comparison, okay. Okay, logistic regression, we already did a number of examples, is it? So it's quite familiar. So for logistic regression, so we initiate our logistic regression object, okay? And for logistic, they have different solvers, okay? And then over here, the first step we do is we apply the PCA, is it? To reduce our data's number of features, is it? So this is the PCA part. Okay, after the PCA part, you get the training data. You need to transform to convert the training data. So basically here you convert training data to features that from original feature space that to reduced feature space. Okay, and we already convert that projected basically. So here basically the convert is projected. And then you can call the logistic regression to fit, but fit with the converted data. Okay. With the converted data, then we can apply also to testing. Testing, be careful, okay, you also need to apply to transform first, convert first, okay, for testing features, testing data's feature. Then you can apply logistic to do the prediction on the testing data. So here we pick a specific sample, this is the first sample in the testing data, and then we test it. Is it? And here we also test the top 10, is it the predicted value. And here is the original top 10. And if you compare, looks like it's pretty good, as it matches. Among the top 10, looks like there is no error. And of course, we, generally speaking, for after our training and testing, we need to see the accuracy, okay, to measure models performance, okay. Measure models are a number of ways, and the accuracy is one of it. And over here is with testing. So this is models, and this is original. That, and you just call logistic regression score, and then it will give you the score. Okay. Okay, so we can see there's not too much that with sklearn if we try to use PCA. That, so just add one more step. And what next one try to show is linear discriminant analysis. Okay, the LDA one. So you also need to import the respective package. And then over here, so you can also initiate, you specify the number of components. Is it like 2 or 3 or 100 something? Is it? Then you can fit the data. Is it to transform the data? And this time we apply the LDA. So the converted data with LDA to do the logistic regression. Is it? And then we also do transform for our testing data, and we can test the result. And then we can also predict the top 10, is it? And then you can compare, is it? But overall, the score for the LDAs, if we compare with the PCA, it's not as good, is it? Its accuracy got lowered quite a lot. Okay. So this is regarding the MNIST example. And what is the next one? Let's take a look. Okay, let's take a look. This one is about some wine data. Okay, also use PCA, LDA. So let's take a look at here, explain more, okay, the idea. So the first step, we already quite familiar that about the how to get data from CSV file, is it, and get the column, is it, assign column to each feature. And then as usual, we do train test split, okay? So nothing new. And over here, we also do the feature scaling. This is regarding feature scaling. And we use a standard scaler, okay? If you recall, we discussed two ways. One is normalized, that the other is standardized. Okay, with standardized, the value is it regarding the mean, so how far away it's from the mean, that's regarding standardization. And normalize is we have maximum, minimum. Normalization is bring data to 0 to 1 range, okay? So anyway, so here we are going to do data feature scaling first. Is it then the same thing we need to transform and feature transform and transform for testing. For training, it's a fit and transform, okay, both steps. And next, over here, and for NumPy package, okay, NumPy package, it provides you the way to do eigenvalue, okay. So eigenvalue and eigenvector. So it can, if you have a matrix, and here the matrix is a covariance matrix for PCA. If you recall, that is a covariance matrix. So it will automatically give you the eigenvalue and the eigenvector, okay? So in this case, it depends on how many features it has. So we can go back to take a look. How many features? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have, there are 13 features. That so correspondingly for the respective covariance matrix, then there are going to be 13 eigenvalues. Okay, and if you 1, 2, 3, 4, 5, 6, yeah, there are 13 eigenvalues. So the NumPy, this function, the eigenfunction from linear algebra, is that it will tell you the respective eigenvalues. And you can also calculate the total unexplained variance. So this is a total variance, okay, for the covariance matrix, okay, and then you can sort it down. And we can also do cumulative. And this is what this is, a list comprehension. So basically it will generate the list with all of the eigenvalues, but sorted, because for this one, it may not be sorted, and this is going to be sorted and then provide you as a list. Okay, then we are going to do the plotting, and this time we are going to plot each. So each variance, the eigenvalues, and we are also going to do the cumulative one. Okay, and then we can see the explained variance and the principal components index relationship. Okay, so let's see. So for this plotting, so here is component index, the total we have 13, and here is the explained variance ratio, so the percentage, so you can see this is the first one, it takes almost it's above 0.38-ish, something like that, is it? And the second one, it's about 0, maybe 18-ish, is it? And here it gives the cumulative ones, is it cumulative? And here it's each individual, the principal component, and its respective variance part, is it? The percentage in the total variance part, okay? So this is about the explain variance plotting. And then what next? So in our previous exam, we didn't go to this much detail, okay? So here just try to show the much more detail regarding the theoretical, the eigenvalue and the eigenvector, okay? So regarding the eigenvalues, is it? We can also get the eigenvectors, okay, eigenvectors. So we can then pair them, is it? Pair them, and we also do the sorting, okay. The sorting, because we are going to use eigenvector. So eigenvector then can be used to build, to construct the transform matrix. Basically, it's the projection matrix. You're going to use eigenvector to build the projection matrix, is it? So that's how we come up with that projection matrix, okay. And then you can also, so once you have the projection matrix, then each of the sample data, is it? Your data product, the projection matrix, then it's going to be projected, is it? So that's the projected values, the converted values. And then what next one try to show is, then we are going to do the scattered plotting of the data samples. But this time it's in what? In the principal component coordinate system, is it? In its respective principal component. So then let's see. So over here, it's about all of the data, is it? So this is the first principle, and this is the second principle. You can see, is it? Along the first principle, the variance is spread out much more, is it? And also its classification is also much better, is it? With the second one, if you project to the second one, is it? It's not that, because the red one and the green one, it's also kind of mingled together, is it? So, but if you project the first one, project the sample to the first one, part of the samples from different classes can be classified quite well, is it? But of course, there are some also not quite well, is it? Okay, and what next one try to see is we use the original number keep of the principles, is it? Number of the principle. And over here is the next one. If you recall the previous one, we can plug in with the percentage, is it? You can also just specify the number of components. Here says, okay, I just want to use 2 number of components. Just keep the top 2 number of components, is it? For our training and testing, then you can do the training and testing data projection. So this is projected data. Okay, after projected data, and over here we just keep the first 2 principles. And here is the plotting for the first 2 principles. Okay, and then what is the next? If you recall, we already did this quite a lot. Is it the plotting, the decision region? Is it with our specified training model? Is it so? And over here, what we did is we use our okay, so let's see what we call. Okay, oh, so that's going to be later on. So later on, what we call here is the logistic regression we are going to pass in. But for this logistic regression, what we first do is do the PCA, okay, to reduce dimension. Is it? And then for the training and testing data, you confirm. You project the data. So project data to new reduced feature space. And then we apply, like in this case, is logistic regression model. That's what this part is. It then you apply the projected data to the logistic regression. Okay, so for this logistic regression, then we call that plot decision region that we plug in with this model. Okay, and then let's see how good it is. So with the result, you can see it is pretty good, is it? So most of the samples are classified correctly. Okay, so it's pretty good. Okay, and what the next one try to show is about the LDA. Okay, the linear discriminator one. And also here, same thing. We just apply the top two principal components. Okay, and then same thing. Over here, we do the logistic regression, and then we feed the data, feed the data. And then over here, what we try to do is we also call that plot. But this is on the training data, okay, with the logistic regression, not to the testing data. And then we can see with the training data, it's also pretty good, okay. So for this case. Okay, and then we do the testing. Is it for the linear discriminant analysis? And we also do the plotting. And with LD1 for the testing one, then we can see the result is also pretty good, okay, in this case. Okay, so the above discussed about linear. Okay, linear ones, okay, linear mapping. And then what is the next one is for non-linear. Is it? So PCA and LDA itself is regarding linear. Okay, if you want to do non-linear, then we need to do the KernelPCA. Okay. So for KernelPCA, so this concept is similar as if you recall for SVM. Is it? We also learned the kernel concept, kernel trick. Is it to deal with the non-linear separable one, separable ones? Is it? So here, similar concept for PCA. If the data is non-linear, is it? Then we can also use the kernel idea. So here for the data set, we just, sklearn also provide you some method to generate a different shape of data. Okay, here is moon shape of data. Okay, then it's automatically randomly generated some data. Okay, 100 samples. And After we generate, okay, and then we apply kernel PCA, and we specify here just the top two components. And then we also specify the kernel. If you recall previously, we also discussed there are a number of ways to pick a kernel. Okay, so this is one of it. And also with kernel, you also need to specify the gamma values. Okay, so because this is related with the kernel function. Okay, after that, then we can transform, so project the data. Okay, and then we do this plotting of the data with projected data. Okay, and then let's see. So for this projected data, you can clearly see is it when it projected to these two principles, it's clearly separable. Is it along the first principle? Is it, of course, along the second, it's really bad. It's completely overlapped with each other. But for the first one, it's clearly you can classify the two different group of data. Is it? Okay, so that's all of the examples regarding the dimensionality reduction. Okay, so the PCA. So basically, that's all about dimensionality reduction. So we started